Now, in this video, we are going to understand multi-classification. Now, the only difference between multi-classification and binary classification is the target class outcome, whereby for binary, the outcome is 2, and for multi-classification, the outcome is more than 2. The same processes involved for binary classification is involved for multi-classification. So for this video, we are going to be exploring the data set of diabetics for the multi-classification. So we load in the data set. Loading the data set, so you can see we have the ID, number of partition, gender, age, urea, CR. These are all the features for what? Diabetics to predict the class, which is the outcome. So in this case, class is the target outcome. So we want to predict what class of diabetics it falls under. So first, let's check for missing value. Let's see if the data is clean. So we say df dot is null dot sum. So you can see that the data set is clean. So let's check the target class. Let's see to figure out maybe the class is balanced or it's not balanced, because for classification, like I used to say, the one problem about classification tags is target class imbalance. If the class is not balanced, the accuracy is not going to perform better, because it's going to learn well from one class compared to the other class outcome. So let's check. So we say df the column of class dot value underscore count. Okay, so you can see we have yn, pyn, then we have 843, 102, 53. You can see we have y 2 times and n 2 times. So that means there's a duplicate. There's a what? Duplicate. So let's check and let's see how we can deal with the duplicate. Dot unique. Let's see where the duplicate is coming from. Okay, so you can see this y has space and this n has what? Space. So what are we going to do? We are going to replace them to match up with the n without space and y without what? Without space. So we say df class dot replace df class dot replace anyway you see n with space, replace it with n without what? Without space. The same thing for y. Anyway you see y with space, rename it to y without what? Space. And we say in place equals to true to authorize the what? The operation. So let's check the unique again and let's see if everything is okay. Okay, so you can see everything is okay. So let's check the value count again to inspect the class balancing value now. So that when we want to balance, we know how to balance it. So you can see for y we have 844, for n we have 103, and for p we have what? 53. So it simply means the target outcome is not balanced. Now we have to balance it up. We have to what? So we are going to be using the random oversampling to balance it up. The random oversampling. So we say from Scikit-learn dot utils import the sample. Then we separate data. I said y equals to df the column of class equals to y. Then I do the same thing for p and n. So I say p, and the column of class equals to p. Then we have n. Then we say the column of class, select what? The n value. So now we are only sampling n and p. So let's say p balance, p that I want to balance, or p sample. Let's use sample. So p sample equal to sample. So where are we resampling for? We're resampling for p. What will be the numbers of samples? The numbers of samples is going to be 844, because we are randomly oversampling both p and what? N. So I'm going to do the same thing for n. I'm going to do the same thing for n. So n sample, then I'm sampling from what? From n, then the total number of sample is what? So I'm going to join 3 of them together. I'm going to join 3 of them to what? Together to form one data frame back. So say df now by equals to pd dot concatenate y that we did not sample, then p underscore sample n underscore sample. Then we shuffle it. So we say df equals to df dot sample, and we say fraction equals to 100, meaning you should shuffle the 100%. So let's check the value count again. You will see we now have our class what all of them what balance. So you can see 844, 844, 844. So it gives us more data compared to the previous shape that we have. So class balancing is good. So if you try class balancing and you don't still have a better accuracy, then that means the issue will be from the data. Okay, so since we balance the class, we can now convert the numerical columns to what? Categorical columns. You know, we said if you don't convert them, there's no how the machine learning algorithm can understand what them. So we have to convert those strange object-like columns to numeric. So there are just two in this data, which is the gender and the what and the class. So let's activate our encoder now. Say encoder equal to label encoder. Say column, we just have only the column of gender and class. I will say for x in whole, then we'll say df x. So match the column with the df, go to df and look for that exact column, equal to encoder dot fit underscore transform df x. So let's see how our data looks like now. So say df dot head. So you can see our data is what is prepared. Now for machine learning tasks, we don't need ID. As long as only data analysis we want to do, maybe visualization, so we can say, okay, let's use ID to know maybe the total number of registered patients. But this is a machine learning task, so we don't need ID. So we are going to drop it out when we are separating the independent variable from the dependent variable, which is the next step. So the next step is for us to what separate what the independent variable from the dependent variable. So we say let x represent the independent variable. Then we say df dot drop. We are dropping two things out from the data that will be assigned to x. Drop id, then you also drop the target variable, which is what? Class. Then y now is going to be the dependent variable. So let y be the dependent variable. So we say here the column of class. So let's split our data into two parts, one for training, one for testing. So we say x train, x test, y train, y train, y test equals to train, test lead, x and y. Then let the test size be 20%. So say test size 0.2, which is 20%. So let's execute that. So at this point, we are good to go. I have an error. It says not found. Oh, I didn't set axis to 1 to indicate that it's going to find these two columns from what? From the column axis, not row axis. Okay, so let's run it again. So now we cannot build the model. So the first model we are going to examine is the base logistic regression. So we say model 1 equal to logistic regression. The model 1 equals to logistic regression. Then we say solver is Newton CG. Then we say model 1 dot fit x train and y train. Okay, so at this point, the model has learned properly from the existing data. So let's evaluate it before we can say, okay, this particular model is good enough to be deployed for this particular what task. So first thing we're going to predict. So we say predict 1 equals to model 1 dot fit or dot predict rather dot predict x test. Then let's evaluate. So we say print classification report of y test and the predicted outcome. So we'll do the same thing for the accuracy, precision, recall F1 score. So say accuracy score, recall score. Then for the recall score, since it's a multi-classification, we set average, we weigh the average, we weigh the average. So we do the same thing for the precision and recall too. We do the same thing for the precision and recall. For the precision and F1 score rather, because we've already looked for the recall. So we say precision score, then we have the F1 score. So let's compute the confusion matrix to check the error. So we say CM equals to confusion matrix of Y test and we predict 1. Then we say SNS dot heatmap of the confusion matrix. We'll say R naught equals to FMT, which is format, equals to 0.5G, meaning the length of the value on the heatmap box cannot be more than what? 5. Okay, so you can see for the logistic regression, we have 89% accuracy, which is very, very okay. 89% accuracy. Then for the other metrics too, we have 89% accuracy. You can see the confusion metrics. We use the recall. This we call to compute the confusion metrics. All these ones on the diagonal are the true outcome. Then, like I said, all the ones surrounding are the errors. So as you can see, we have minimal error. We have minimal what? Minimal error. So let's check out another algorithm, which is the decision tree. So let me just copy up algorithm. Then let's change this to decision tree. We say we want to change this to decision tree classifier, then we run it. What does it say? Oh, I didn't close the bracket open first. Okay, so let's evaluate the decision tree classifier and let's see the difference between the decision tree and the logistic regression. Which model learns better from the data and evaluate the data properly. So you can see for this we have 99% accuracy. So you can see we have just one error. So 99% what accuracy. So overall, the decision tree performs better on this data set compared to the what logistic regression. Still okay, logistic regression still perform better, but not up to the level of what decision tree regressor. We see in our next video.